Okay. You boleh nampak skrin ni ke?
Boleh, boleh.
Boleh Okay, I think we should do it now. Okay, today we're talking about transducer electrochemistry, which focuses on glucose biosensor. Okay, last week we did the principle of electrochemistry, and then we did some electroanalytical techniques. So this week kita akan apply those techniques in some of the sensors. Yeah, the most popular sensor, which is a glucose biosensor. So glucose biosensor ni untuk apa sebenarnya? If you can think of one of the applications of glucose biosensor. Any idea? The applications of glucose biosensor in daily lives. Any idea, guys?
To check the blood sugar level.
To check your blood sugar level. Okay. So kenapa? Why should we monitor them?
Diabetic patients.
For diabetic. I see. Let's say katakanlah if you're diagnosed with diabetes, kenapa kita kena suntik insulin?
Because the body
Yeah.
cannot produce insulin naturally.
So because our body cannot produce the insulin ourselves. And that is because, sebab apa kita tak boleh produce sendiri? Insulin tu. Sepatutnya if you're healthy, are we able to produce insulin ourselves? Boleh ke?
Yes.
If we are healthy.
Yes, doctor.
Boleh Tapi kenapa kita tak boleh produce kalau apa sebab dia? What are the causes yang menyebabkan kita tak boleh produce insulin in our own bodies, that we need help from outside? Let's say we have to inject ourselves with needles and whatsoever every day. Every day ke kalau insulin ni, kalau penyakit yang dah kronik, do we have to inject ourselves every day?
Maybe.
Maybe. Have you seen anyone doing that to themselves? Injecting themselves with needles? Pernah tengok?
No. Luckily.
I've seen it so many times in front of me. Dia akan inject diri dia sendiri. Saya pun terperanjat mula-mula. Okay, anyway, there are three parts of this lecture. The first generation, second generation, and the third generation of glucose biosensor. So we'll start with the first one. Okay, at the end of this chapter, we are supposed to be able to, number one, we must know how to explain and illustrate the principles and applications of electrochemical transducer for glucose biosensor. Number two, we need to be able to describe and distinguish. Maksudnya kena bezakan, you have to be able to differentiate all these three different generation of glucose biosensor. The first one, the second one, and the third one. Right? Okay, now we talk about the transducer. Okay, if you remember, you did lectures with Dr. Shafinas about the components of a biosensor. What makes a biosensor? What are the components? What are the main keys in constructing a biosensor? What do we need? Kita perlukan apa? What do we need, guys?
Biosensing element.
Again?
Biosensing element, transducer,
Transducer,
and
the final one, so that you can see the signal.
Oh.
Is it just two? Biosensing element and the transducer?
And the device. I don't.
What was the third one?
Forgot.
Anyone? Cepat tengok nota. Sensing element. Right?
Microprocessor.
Processor. So processor, so that, well, why do we need a processor for? So that you can see the signals, yeah? Late, yeah? Remember that. Okay, a transducer is one of those main components in a biosensor that is responsible to convert a reaction, or in a technical term, we call it a biorecognition event. A reaction between what? Between the bioelements, the sensing elements, with the substrate of whatever molecule or whatever you're trying to detect or to sense into a measurable signal. If you know that something has happened, but you do not know, we cannot tell what the signal is, then kita takkan tahu kan macam mana kita nak detect. So we need something that is measurable in terms of the signals. So if you get the signals, these measurable signals will correlate with the quantity or the presence of the chemical or the biological target of interest that you're trying to look at. Okay. So have we done this before? There are 4 different types of transducers. Yeah, we talk about potentiometric, we talk about voltammetric, amperometric, and conductimetric. Okay. Potentiometric is about the measurement of a cell potential. So we're measuring the voltage. Yeah, so that voltage is your signal, and you fix at 0 current. So if you remember EMF, what is EMF again? What force is that? Electro what?
Electromotive force.
Electromotive force that is proportional to the logarithm of the concentration of analyte. So in other words, whatever whatever you detect, your potential, your voltage will be proportional to the concentration of your analyte, your target molecule. So that is potentiometric. Then we have a voltammetric. Voltammetric is about increasing potential. You apply the increasing potential. You apply it to the cell's electrode until you see oxidation or reduction of the target molecule, and then you will start seeing a sharp rise. Remember the peak uh, or decrease in cell current. That peak is actually telling you the value of the current, how much you have those molecules inside your cell. So the height of the peak current is directly proportional to the concentration of your analytes. Okay, if oxidation or reduction potential is known, your step potential is directly proportional to that value, and what you're measuring is the current. So still, if you remember the difference between voltammetric and amperometric, they are all in the same group. Apa beza dia voltammetric dengan amperometric? Voltammetric dengan amperometric. They both measure electrical currents. Tapi apa beza dia? Ada beza sikit ke? What's that? Amperometric? Siapa-siapa ingat? Minasan, daijoubu desu ka? Ni kena keluar sedikit pun ni. Baru dia faham kot. Minasan, kiitemasu ka ne? Are you listening? Junkiat, are you there? What's the difference between voltammetric and amperometric?
I think from the note, voltammetry is the measure the current at varying potential.
Yes.
Amperometry also measure current, but as a function of time.
Okay.
Electropotential. Is it like electrochemical cell?
Okay, amperometric, you fix the potential and then you measure the current. Voltammetric, you don't fix it. You keep, you have a potential range. Remember the potential window, the term potential window. You fix a range of potential voltage that you want to apply to the cell, and then you measure your current. Still measuring current. Okay, thank you. Okay, conductometry is about measuring how easy can electrical current go through a what? Through an ion-containing solution. So you are measuring the magnitude of conductance, conductivity. Yeah? We talk about conductivity due to chemical or biochemical reactions. So this is conductometry. Okay. Now we look at electrochemical transducers. Electrochemical transducers, which encompass amperometry and potentiometry, are the most established transduction method for biosensors. So mana-mana pun kalau you buat, if you deal with biosensors, mesti ada. It's either amperometry ataupun potentiometry. You cannot run away from this because in real applications, let's say in a hospital, in the lab, in a food production factories, you need sensors, right? You need biosensors to detect a lot of things. So without signals, without measurable signals, I mean, now we are all talk about digital, right? Kita tak boleh dah tengok jarum-jarum ke macam tu. Tak. Now we have to integrate these reactions with the electrochemistry so that you can see the signals in numbers. Nampak dekat screen, okay, pH berapa, okay, ini berapa current berapa, then you know berapa concentration you punya, let's say contamination, let's say kan, macam itulah. So amperometry biosensors function by the production of current when what? When is that? When a potential is applied between two electrodes. Electrode apa? Working electrodes and reference. The other one, which was the counter electrode, is an electrode that is introduced into the system to minimize the noise. Remember, ada tiga kan kita dah buat hari itu. There are three types of electrodes in the system. Working electrode, the one that is responsible to do the biorecognition, to do the sensing. Number two is the reference electrode, and then the third one is the counter electrode. Okay. Okay. Now we look at Clark oxygen electrode. Okay. This is a very popular electrode which was invented so many years ago. This was the beginning. This was one of the biosensors that were invented in the first yang generation lah, maknanya yang dulu-dulu lah sebelum ada yang sensor-sensor yang hebat-hebat dan canggih-canggih seperti sekarang. Clark oxygen electrode ni adalah yang paling popular lah, that is in the history. So it is the simplest amperometric biosensors in common usage. It consists of a platinum cathode. Remember what is cathode, what is anode, at which oxygen is reduced. Kat situ disebut apa? At the cathode, oxygen is reduced. And a silver chloride reference electrode. This is just a reference electrode. Okay, we look at the reaction. At the anode, there is a glucose oxidation reaction. So you see, there is oxygen there. In this part, left-hand side here, is the reactants. Whatever is reacting, the starting materials. So you have a glucose, which is your target molecule, because we talk about glucose biosensors, right? So glucose is interacting with your oxygen in the presence of some water molecules. And this reaction is being catalyzed by a glucose oxidase. And then you produce gluconic acid, this one here, in the orange box. And there's another byproduct, which is the hydrogen peroxide, H2O2. So at the platinum cathode, so there is operation tadi, reduction, right? So oxygen receives 2 electrons, remember? In electrochemistry, oxygen and reduction is defined as what? Apa beza electrochemical reduction, oxygen and reduction in electrochemistry and oxygen and reduction in chemistry, in common chemistry? Apa beza dia? In terms of electrons, remember? This is very important. Hong Chun? Hong Chun Kiat?
Yes,
Dia bagi saya
Doctor.
satu nama, give me one name. Panggil je.
Desmond Tan.
Okay, Desmond. Desmond tengah sahur kot. Desmond Tan. Imaskan ada ke tak ada ni? Dia tak jawab lah Hong Chun. Chun Kiat. Another name. Panggil lagi satu nama Hong
Astrid.
Chun Kiat. Siapa?
Astrid.
Okay. Siapa yang dia panggil tu saya tak dengar. Mana you all ni? Saya panggil Abelina lah. Abelina ada Abelina?
Yes, doctor.
Hi Abelina.
Hi, doctor. Good
Are you
morning.
okay?
Yeah, I'm okay, doctor. Thank you
Okay.
for asking.
Okay. My question was, what is the definition of oxidation reduction in terms of in the field of electrochemistry? Apa beza dengan chemistry biasa tu, oxidation tu? Oxidation reduction in apa beza dia?
Oxidation means it's when the reactants, they accept the oxygen, which means
Okay. Okay. This in terms of oxygen, yeah. Okay.
yeah, doctor.
Oxygen and hydrogen. Okay. In electrochemistry?
Which means in electrochemistry, which means they donates the electrons to the other molecules. So
Okay.
when the reactants donates the molecule, the electrons,
Yeah.
so which means the chemical reactions presents the oxidation process, whereas the reaction, the reactants, they gain the electrons from the reactant. Yeah.
Right. Correct.
Okay, doctor.
Okay, guys, remember kita buat sikit revision kan? Electrochemistry, oxidation and reduction in electrochemistry refers to the electrons, whether you are donating or you're receiving. If you're donating, then you're being oxidized. If you're receiving, then you're said to be reduced. Yeah, remember this? So in this context, at the cathode, there's a reduction. At the anode, there is an oxidation. Oxidation means here you are talking about the oxidation in terms of oxygen. At the cathode, there's a reduction because there are 2 electrons being received there. Yeah. So oxygen consumption is followed by oxygen electrochemical reduction at the platinum electrode. So this generates an electrical current. That is why we call it amperometrics, but we are measuring the current. So in amperometric biosensors, electric potential is used to drive a redox reaction because here, remember redox reaction, both oxidation and reduction taking place at the same time, and the current resulting from that reaction is measured. So your signal now is in the form of current. Current is measured in, what is the unit? Amps, ampere. So recall that, remember that, redox reactions involve the movement of electrons. The current flowing is directly proportional to the analyte concentration. Remember, current is defined as the number of electrons flowing in 1 second. The more current flowing means you're getting more current. So the more current, the more analyte that you are detecting. So in principle, any species that can be oxidized or reduced can be empirimetrically or voltammetrically detected. So setelah ini soalan tanya kan, what are the criteria for any chemicals of any target molecules to be detected? Syarat dia mesti, apa syarat dia? It has to be able to be oxidized or reduced so that you can produce a signal that can be detected. So the first biosensors is an oxygen-based electrodes. It's an enzyme electrode, which on the surface of the electrode you immobilize your enzymes. It is the first described by siapa yang buat ni? Clark and Lyons in 1962 they constructed this biosensor to detect glucose. So oxygen-based electrodes is the most studied and developed biosensor application. So in early biosensors, oxygen was used as oxidizing agent. Remember, oxidizing agent, reducing agent. Okay, so the consumption of oxygen is followed by electrochemical reduction at the platinum electrode, as shown is figure 1. So let's have a look at figure 1. So this is the schematic diagram of the electrode. So you see here, oxygen electrode has oxygen permeable membrane. So membrane ni dibuat daripada apa? Ada 3 jenis. There are 3 different materials that been used to construct this membrane, which is PTFE, Teflon ni. Kat sini yang pertama sekali, if you see it, this one is PTFE, polytetrafluoroethylene, if I'm not mistaken. And then polythene, the second one here. Polythene is normally used to sebagai apa, waterproof material. Selalunya dekat bangunan kan, dia tak nak ada any apa humidity ke apa, you akan pasang this membrane supaya tidak ada berlakunya mengelakkan apa orang kata kulat ke kan. Then we have a cellophane, the third one here, macam you buat cellophane tape kan. So these are the material that is covering the electrodes. So a layer of enzyme is placed over this kat sini ya. So you akan letakkan you punya enzyme, you immobilize them, and then it's being held in place with the second membrane such as cellulose acetate. If you want to know more, you please Google what are the materials for so that you can understand more. So this is the basic of the first oxygen-based electrode, yeah, to detect glucose. Okay, the substrate, if you look at, this is how it works. The substrate, your target molecule, and oxygen, it goes into the first membrane. Yeah, this is the first membrane, second membrane, M1, M2. M1 is a membrane 1, membrane 2. They react with enzymes to form products. So only oxygen remaining will penetrate the second membrane to be measured by the electrode. Okay. Okay, this is a simple empirimetric biosensor. What you do here, you apply a potential about minus 0.7 volt. Remember the why do we need a potential for? Ingat tak? Potential difference. The more difference between 2 electrodes, the more force that you are imposing on the system. Okay, in this case, we applied about minus 0.7. This will generate a current which is carried between the electrodes by means of a saturated potassium chloride. This is another electrode, yeah? Okay, this electrode compartment is separated from the biocatalyst. So what is your biocatalyst here? It is a glucose oxidase, GOD, by a thin plastic membrane permeable only to oxygen. Because we're talking about oxygen, only oxygen should go through the system. So everything that happens is based on interaction of oxygen with the molecules inside your cell. Yeah. So the analyte solution is separated from the biocatalyst, which is glucose oxidase, by another membrane that is permeable to the substrate and product. So it's all about membranes, it's all about oxygen, it's all about what is interacting with what. So that you should focus on those. So, but there is a problem with the first generation of this biosensor. Ada beberapa kekurangan dia lah. There are some of the drawbacks are um, there are interference when we do biosensing. When we do sensing, we have to to minimize the interference gangguan ataupun if you have lots of interference, then your signal may not be accurate or correct. So interference from other materials due to high reduction. Yeah, oxygen is very easy, can be easily interacting. Yeah, can a very interactive molecule. Uh, so oxygen can be reduced, oxygen can be oxidized. So that is the kekurangan dia lah, sebab it limits, it gives a lot of interferences from these properties of oxygen. So we need to solve this problem. So in order to solve the problem, we measure the oxidation of your peroxide. So peroxide is your another interference in the reaction. Remember in the reaction scheme, the byproducts of the first glucose biosensor was hydrogen peroxide, which is H2O2. So H2O2 is the interfering gas. Yeah. So to solve this problem, they set the electrode potential. Mula-mula dia letak minus 0.7. Now they fix it at plus 0.65 volts. But selepas dia buat ni, there's another problem, which is they getting interference from ascorbic acid pula. So there's another problem. There is another product that is being produced in the system. The ascorbic acid is actually a vitamin C. If you look at here, it's basically if you go to pharmacies, the departmental store, drugstore, you will see ascorbic acid is sold as vitamin C lah. So the vitamin C, the ascorbic acid itself is oxidized at this potential at plus 0.665, and commonly, because ascorbic acid is commonly present in biological samples. Kalau you hantar any biological sample, biasanya you akan dapat detect ascorbic acid. So ascorbic acid ni akan beri you interference in terms of the signals. So bila ada interference, your data akan jadi tak accurate. Another problem with the first generation of glucose biosensor is remember the hydrogen peroxide, due to the reduction of oxygen at the platinum electrodes, and then it degrades. Bila ada banyak sangat hydrogen peroxide terhasil at the cathode, then it is actually damaging, it is degrading the enzyme. So hydrogen peroxide is a gas, it's a very corrosive gas that is damaging your electrode. So that is not good. But the third one is the ambient oxygen levels, because you need oxygen, only oxygen, dissolved oxygen inside your cell. The oxygen levels has to be controlled at all times and kept very constant. So this is very tedious and very impractical. So inilah masalah-masalah dengan the problems with the first generation. So in order to solve this problem, they replace oxygen with another oxidizing agents. Ada beberapa lah, then we will see what they are. And then we will go into the second generation of a biosensor, glucose biosensor. Okay, so far, That was the first generation. So we go into the second generation now. Okay, second generation glucose biosensor is based on a mediator. Mediator is something that is mediating. In other words, we say mediate means in between. That is facilitating. Ya, orang tengah. Yeah. So the major problem with the first generation of biosensors is their dependence on the dissolved oxygen concentration. Remember I said that just now? This problem with the dissolved oxygen concentration can be overcome by applying mediators or redox mediators in the system. So redox mediators transfer the electrons directly to the electrode by passing the reduction of the oxygen co-substrate. Okay, so the main point in here is the mediators are replacing oxygen as oxidizing agent. Remember, the oxidizing agent is something that is oxidizing something that causes some other species to be oxidized to produce electrons in the system. So in the second generation phase, this step, okay, this step here, number 2, where you are producing hydrogen peroxide, there is no more this. Yeah, this has been skipped. So this is your hydrogen peroxide. It's a mild antiseptic that we use in medical and in the labs. Yeah. So this is just about oxidizing agent. If you look at the definition again, oxidizing agent. We have an X and Y. Y gains electron, it becomes more negative. Okay, this is just a definition. I don't want to talk about this. Okay, the principle of electrochemical biosensors, again, we have a substrate, we have the product, you have this enzyme label with your mediator, which is ferrocene. This is your electrode, and then you apply voltage to the system so that the reaction will take place, because this reaction is not spontaneous. Remember, if you have a spontaneous reaction, that cell is called voltaic cell, but this is not voltaic cell. This is a electrochemical cell. So you need to apply forces. You kena bagi tenaga pada sistem tu, then they will interact and produce reaction and produce signals. Yeah. Okay, this is about measuring current, which is proportional to the concentration of whatever substrate that you are looking at. Okay, so most sensors use enzyme which is called glucose oxidase. Biasanya glucose oxidase ni apa dia punya applications dia? Anyone? Boleh tak cerita sikit pasal glucose oxidase ni? Maybe something about the facts that you know, yang you tahu pasal glucose oxidase. Biasa guna kat mana Kenapa kita nak ada glucose oxidase ni? Saya tanya, I'm gonna ask Rajano Syairah. Syairah boleh tolong saya? Can you share with us, Syairah? Syairah-san, imasu ka ne? Ada tak? Rajano Syairah ada tak? No, ada answer. Okay, Amira? Amira Munshi ada?
Ada doktor.
Okay, Amira, biasa kita guna glucose oxidase ni masa bila? Glucose oxidase, it's an enzyme. Enzyme ni dia very popular kan? Untuk apa?
Glucose oxidase function dia untuk remove oxygen from food product.
untuk oxidize ataupun untuk
To
reduce.
remove, remove small amount of oxygen.
Okay. So apa sebenarnya kita nak hasilkan bila kita gunakan oxidase ni, glucose oxidase? Dia spesifik ke?
Saya tak sure.
Enzim ni? Enzim ni adakah boleh, let's say you ada maltose, you ada galactose, boleh tak glucose oxidase ni jadi catalyst in your reaction?
I think it's only glucose.
Dia akan target pada glucose Okay. Okay, most sensors are constructed on electrodes and use a mediator to carry electrons from enzyme to electrode. Remember, in order for electrons to transfer, they need a carrier ataupun dia kena transfer dari mana? From the electrode surface kan? Nak masuk ke external wire. And circuit tu, macam mana dia nak transfer? Because they are not in the same phase kan? Jadi dia perlu ada satu mediator. Mediator tu yang akan tolong bawakan elektron. So let's say you have an oxidation process taking place, and then you produce oxygen, right? You produce electrons. So those electrons need to transfer to get out of the electrode surface. So someone has to help, and that helper is your mediator. Dia akan bawa keluar. So in this case, you're talking about ferrocene. Ferrocene is an iron complex. So this is how it works here. Ferrocene will be oxidized, and then dia akan sambung lah, and will continue with the reaction here in this part. So only then you will get your electrons flowing in the system. Then you will get your signals to be measured. So if you look at here, this is the catalytic enzyme electrochemistry untuk ferrocene. Okay, kat sini dia ada ferrocene saja, and this one ferrocene plus glucose. So you have a different kind of signals kat sini This is just trying to tell you that electrons are being shuttled or being transferred bila you menggunakan ferrocene as a mediator. Kat sini that's the main point lah. So actually, apa sebenarnya mediator ni? What are mediators? So mediators are agents that are responsible to transfer electrons. To transfer electrons. Yang bagusnya, mediators, they are reversible in terms of. So reversible tu apa? It can go through oxidation, and then it goes back to the reduction. Maksudnya dia boleh pergi. It's reversible. It is reversible. So mediators have a suitable oxidation potential, about 0.1 volts up to 0.6 volts. The concentration could be controlled. Kalau you bezakan dengan oxygen concentration is very difficult to control. The transition metal cations, because they are complex compounds, biasanya akan ada satu metal ion in the middle. So in this case, we'll talk about iron. Iron can form so many complexes, such as hexacyanoferrates or ferricyanide. You can also have ferrocenes, which is the most successful sandwiches. Actually, it looks like a sandwich of iron between two anions. If you see this is your anion, this is another anion, this is your cation. Remember, cation is positively charged and anions are negatively charged. So they are being sandwiched by these two anions. So that makes it complex. So why we use ferrocene? If you look here in the journals, you can find that ferrocene being used quite often in biosensors, but 23% of the most currently available biosensors use mediators that made of ferrocene, using ferrocene as their mediators. Others could be osmium complexes. Some of them uses quinones. Some uses phthalocyanins. Some uses organic dyes. You know, they can be used as mediators because they are reversible and they have certain other properties that is being said in the previous slide that is useful in biosensing area. So, what makes a good mediator? Macam mana yang maksudnya yang a good mediator? A good mediator will react rapidly with reduced form of enzyme. Okay, it is reversible. Reversible means in terms of fast electron kinetic transfer kinetics. Remember, uh, last time when we did a voltammetric technique, I told you that uh, for a system to be recognized as reversible, it has the potential difference must be at least, or in the range of 59 or 60 millivolt, the difference between peak and another peak. Remember that? Look at your notes if you don't remember. So other properties are good mediators are it has to be sufficiently soluble. If it doesn't dissolve in your solution in the cell, it is very difficult for you then to do detection. So in both the oxidized and reduced forms, yeah, it has to be soluble. It has to be able to rapidly diffuse between the active site of the enzyme and the electrosurface. Remember, we talked about mass transfer last week. We talked about in order for a reaction to take place, you remember you have your cell. Inside your cell there is your electrode. So inside your cell there is a solution that contains your target molecules. Your target molecules has to travel up to the surface of your electrode. Let's say this is your electrode here, which you immobilize your sensing element. So your target molecules has to travel to the electrode surface so that the interaction can produce a reaction. Once the reaction takes place, then you get a signal because you're producing electrons. Remember that? That was the principle. So one of the main mass transfer is diffusion. Remember diffusion, convection, and then what is the other one? Convection. Convection when you apply a magnetic field or to the solution. Okay, three main mass transfer. Okay, we go back here. A good mediator, this solubility should, however, not be so great as to cause significant loss of a mediator from the biosensors microenvironment to the bulk of the solution. Maksudnya, you don't want it to be too soluble. There is certain limits, certain range of solubility that you need for a mediator. Okay. Then other properties are overpotential for regeneration of oxidized mediator at the electrode should be low and independence of pH. Okay. Then your mediator should be stable in both oxidized and reduced form. Reduced form of biomediator should not readily react with oxygen because normally in the system you will have oxygen interference. If you don't, how do you remove an oxygen in your system? You can do bubbling. You can put other gases such as hydrogen. You can put uh, argon. You know those yang tidak bertindak balas dengan you punya uh, whatever inside your cell. And the last properties is your mediator should be non-toxic. Yeah. Okay. How do we incorporate mediators into a biosensor? So both enzyme and your ferrocene must be immobilized onto the electrode. So the simplest approach, the simplest way of immobilizing an enzyme and fluorescein onto your biosensors is using a carbon paste. Remember the carbon paste? You have a carbon powder. You you put some water inside it, or not, or other organic solvent, and you then you produce a paste. Yeah, bentuk dia macam paste is something like a slurry, something yang macam lembik-lembik sikit lah, tapi it doesn't dissolve. And then your enzyme absorb on the carbon paste, electrode surface, and held in place with the membrane. Lepas you letak, you mobilize your mediator and your enzyme, and then you put a membrane on top of your electrode to make it stable. Yeah. There's another complex approach. Ada yang lagi susah sikit, cari lain. You can use a graphite foil with edge plane exposed coated with ferrocene, dimethyl ferrocene, menggunakan kaedah evaporation. Ya, you akan gunakan toluene. You dissolve your ferrocene inside with toluene, and then you coat them. You letakkan di atas you punya electrode surface. And then you put a glucose oxidase in buffer, then immobilize it on the surface by reaction of this toluene sulfonate. And then you cover your sensor with nucleopore membrane. This is the membrane. Remember, membrane is supposed to be the pores can. There should be permeability. Boleh? It lets something. It is permeable means boleh get it. Allow something to go through it. It depends on what you want it, what the molecules can boleh tembus lah. Macam tadi we talk about oxygen, so only oxygen yang boleh tembus. So for glucose, the operation of the mediator can be represented such as follows. So you have the glucose interacting with your glucose oxidase, and then you're producing gluconolactone and protons. And this is your glucose oxidase. Your glucose oxidase then interact with your ferrocene to produce oxidized form of glucose oxidase, and then you get back your ferrocene. Your ferrocene then will be oxidized to produce Fc plus. Remember the oxidation? Fc oxidation number is 0. Fc plus means it loses 1 electron, so it is being oxidized. So this is the overall from glucose, it becomes gluconolactone. Okay, this reaction is very important. Okay, a ferrocene mediated biosensor for glucose. If you look here, you have your glucose here interacting with FAD, and then you produce a gluconolactone. FAD goes back, yeah, FAD will become FADH2, and then the reaction takes place. This is continuous reaction, yeah. FAD then interact with ferrocenium, and finally you are getting 2 electrodes here that will produce your signals. Inilah yang menyebabkan you akan dapat signal in your system. So oxidation of glucose is carried out by FAD component of glucose oxidase, which is then converted to FADH2. Then FADH2 is reoxidized to FAD by your mediator. So your ferrocene is reoxidized again to directly at the electrode. So the current flowing through the electrode is an amperometric measure of glucose concentration. Because you want to detect glucose concentration, you get the signal in the form of currents. That is why we call it amperometric. Okay. First generation, second generation. Okay. A is the first generation of the glucose biosensor. B is your second generation. Your amperometric biosensors for flavoxidase enzyme, illustrating the first and the second generation in the development of a biosensor. The biocatalyst is shown schematically by the cross-hatching. So this is your biocatalyst. A, first generation electrode utilizes hydrogen peroxide produced by the reaction. Remember, the potential is about plus 0.6768 that you produce hydrogen peroxide as the interfering gases in the system. In the second generation, B, the electrode utilizes ferrocene as a mediator to do what? To transfer the electrons produced by the reaction to the electrode. So your potential was set at plus 0.19 volts. So these are the main differences. Okay. So I guess that's it for first and second generation. I think we shall continue with the third generation of glucose biosensor after you guys come back from mid-semester break. Yeah, so the week 9, then we will start with the third generation for the glucose biosensor. So, oh yeah, one thing. This is regarding your lab session. Tadi tu ada yang tanya saya kan, when is the lab session is going to start? So because of the ada orang yang akan balik hari raya kan, and then you guys will be isolated. You go through the isolation process at the college. So I think we cannot do the lab at week 9. Sebenarnya the original plan was to do the lab session soon after the mid-semester break, but sebab you all kena ada yang 10 hari kena isolation, then we need to wait after you dah habis lah, maybe week 10 or week 11. Only then we can start with the lab session. Guys, you guys listening to me? You guys with me?
Yes, doctor.
Semua senyap je ni? Ke ada ke tak ada ni? Dah tak sabar nak balik raya ni. Siapa balik hari ni? Who's going home today? Ada orang balik ke hari ni? Amir Hussein balik bila? Amir ada Amir? Amir Resang. Apalah you ni. Guys, boleh tak you buka kamera sekejap? I want to take pictures with you. Ambil gambar sekejap je. Okay guys, please onkan kamera sekejap. Kita ambil gambar sebelum hari raya lah ni, konon-konon. Can I see you guys? Boleh tak saya nak tengok muka pelajar-pelajar saya yang ceria pagi ni? Itulah nampak macam sedih pula. Kenapa ni? Janganlah sedih. Dekat Mama lah, tengah lab. How is your FYUP? Everything goes well? Ni maksudnya okey ke tak okey?
Maksudnya
saya
okey,
nampak siapa?
doktor. Maksudnya okey, doktor.
Okey, Subashini okey ke? Your FYUP?
No, doctor.
Why no?
Long process to go, cannot finish.
Tak apa, that's a learning process, okay? Don't worry too much. You guys have time. You just have to sabar sikit lah kan? Because there's so many limitations. Ada banyak benda tak boleh buat kan? Tapi at least you try lah. Jangan give up lah. Sempat lagi. Siapa lagi? Eng. Eng buat apa Eng? Navin Eng. Siapa lagi saya nampak kat sini? Clarin.
Yes, doctor.
Clarin, what is your experiment about?
Enzyme characterization.
Oh, exciting. Dah banyak result belum?
Belum.
Belum. Okay, so Farah Nadia? Apa project you? What is your project about?
Optimization, doctor.
Of what?
Metanogen.
Oh, metanogen. Okay. tanya sikit lah. Siapa lagi? Wei Bin. Hai Wei Bin.
Hi, Doktor.
Ada 2 orang ke Wei Bin? Do we have 2 Wei Bin?
Tak ada, satu orang je.
1 orang. Okay. Okay, anyway, good to see you guys. Saya harap you all semua patuh kepada SOP. If you guys are going home, if you guys are going out, remember kat luar sekarang cases are increasing. Please pay attention to yourself lah sebenarnya. You jaga diri you. I really want to see you guys back as a whole. Tak nak ada orang hilang tangan, hilang kepala ke lepas cuti mid semester break. I need to see in one body whole body. Tak nak ada putus tangan ke, telinga sebelah tak ada lepas balik hari raya. Make sure you alive lah lepas balik. Just kidding. Okay, I think last word from me, selamat hari raya kepada yang menyambut hari raya. To those who are staying in the lab at home or doing your FYUP, good luck. Hope to see you guys back after mid-semester break. Okay, and anything we'll just keep in touch in the WhatsApp group. Yang sesiapa yang belum isi lagi survey form untuk reflection on principle of electrochemistry tu, nanti saya akan buka lagi sekali. So tolong isikan, boleh yang tak sempat isi, then I will just extend it. So you boleh buat sikit reflection lah. Okay, I think that's it from me. Thanks again, selamat hari raya. See you guys. Okay, bye.
Thanks,
Bye, Doktor.
Bye guys. Jangan, mata.
Thank you.
Bye.